Good morning. Here we are once again at the physics video lecture. Physics 2A, video lecture 42. I'm going to begin with some announcements, end of semester announcements. I've written down here somewhere. While I still have your attention. So as far as the hours that we have left, so we have this lecture, the second, the fourth, so that's Wednesday and Friday. We have the 7th and the 9th. That's our last lecture, Wednesday. And we have on the 16th, our final exam. Okay, so quiz here, quiz here, and then the 7th is a Monday. The 9th, there's one more quiz on campus. I also decided that the last homework and notes would be due this Friday on the 4th. Quiz plus last homework and notes. Now, 7 and 9, I'll separate this off. So that's Monday and Wednesday. These notes and homework will be really important for you because what is done here can still end up on the final exam, which is just a double quiz. So instead of the 12 minutes, 25, 30 minutes, okay? Take it from that material, and people have turned in and taken such great notes, at least some of you, that you wouldn't want to leave your whole book incomplete. So, but I won't be collecting those, okay? So this will be the last homework and notes. That'll be this Friday. We'll have that quiz. As far as new material goes, today we have chapter 12 that we're going to finish up. And for these 2 days, 4th and the 7th, Friday and Monday, we have chapter 13, very important. And for this day here, we have review. And anything we didn't finish up, and people have questions, and I can do some problems at the board, etc. So that's how it is. I think we made it pretty well because two hours for chapter 13 isn't bad, and that's what we'll end with. Good, so that's our schedule. Quiz, that's today, and finish up chapter 12. Friday, there's a quiz. Friday afternoon, usual schedule, last homework and notes. Then this is Monday and Wednesday of next week. And then we've got the final exam on the 16th. And it's on the syllabus. I think we'll put our quiz up at 9 o'clock, but I'll announce that on this day here. Okay, good. Let's start. Then I had questions, namely about quiz 14. And that was the depth at which a submarine emits a bubble or something like that. It was an ideal gas law problem. So down here at 1 and up here at 2, this is the surface of the water. This is down here at a depth h. And the bubble expands as it goes up. So we just write down the ideal gas law. So we have P1 V1 equals P2 V2. Because the contents of the bubble remain the same, and the temperature we're saying is uniform up there. Good. So the pressure down there, though, is the atmospheric pressure plus density of water, GH. And V1, I'm going to go ahead and write it in terms of the bubble volume. Actually, let's keep it simpler. So we'll just leave the V1 for the moment. And up the top, it's P atmosphere when it breaks the surface, V2. So what we want to do is solve for H. Okay? So we can solve this algebraically for H first, and then we'll deal with those radii. Okay? So we have atmospheric rho GH equals atmospheric pressure V2 divided by V1. And we just have to subtract off the atmospheric pressure divided by rho G. So H is equal to V atmospheric V2 over V1 minus 1. Okay, I subtract that off to the other side. And then we divide this by rho density of water times G. So there's the answer, except that we were talking about radii in the problem and not volumes. Now it's better not to, I started writing out that volume in terms of the radius, but the volumes are going to square as the radii cubed. So we can also write H is equal to P atmosphere divided by density of water times G. And we're going to have here R2 cubed divided by R1 cubed minus 1. And on the quiz, R2 was given as a factor of R1. So I'm just going to write, for example, R2 was equal to, say, 2.5 R1. Okay. And if you do that, you have R2 divided by R1 is equal to 2.5. And since we're looking at it cubed, and so you make that substitution in there, plug the rest of the numbers in, and get your result. Okay, so that's how that quiz went. Okay, so the next question that somebody asked was about problem 1124. Chapter 11, problem 24. So let's have a look at that. Okay, 1124. So that was kinetic energy being converted into heat. So it's a really interesting problem. So you have a car moving at a certain speed. So there's the mass of the car, there's the speed in meters per second squared. That's kinetic energy. And as the car comes to a stop, the brakes are what brought it to a stop. That's the major source of frictional force. Of course, in reality, there's also friction with the road, but we won't worry about that because we're not skidding. So half mv squared is going to be equal to m, choosing a different letter, okay, because it's a different mass, mc change in temperature. So this here is the mass of your car, that's its speed, that's in the problem. This is the mass of those 4 brakes. So that was 4 times 8 equals 32 kilograms. This was the specific heat of iron. Okay. So mass of the car, speed given, 4 of those brakes, cubic of iron. So that's everything that's been given, and you can now solve for the change in temperature. Good, not bad, right? So once you set it up and understand it, then the rest is just an algebraic step. Again, a reason to never plug numbers in until you see what's going on here. So I'll just right here, solve for delta T, that's the change in temperature, and they can get pretty hot. Okay, so this was 1124. Now 1167, somebody also asked about, and that is a really interesting problem. So let's look at it in the following way. We'll even do some colors here. So this is our Earth, has a radius of Earth, and of course the Earth is a sphere. So there's incoming radiation from the sun that's heating up our Earth. On the other hand, the Earth has some temperature, and therefore it's radiating electromagnetic radiation in all directions. So they're a lot cooler than the sun's rays. Okay. So those are the two things that are happening. The Earth is absorbing radiation from the sun, and it radiates energy away just by virtue of it being at a certain temperature. And we have that Stefan Boltzmann Law. And I'm going to go ahead, this picture's so good. I'll leave that up there and make a little space here. So the intensity of the incoming radiation, we have I is given as 960 watts per square meter. And then we have this formula, power radiated in this case is equal to sigma E a temperature to the 4th temperature in Kelvin. Okay, so this is the law of objects radiating away. Now this constant, you just look up. This one, we're just going to assume E is equal to 1. What about this area? Okay, so I'm going to put an equal sign here, and we'll leave some stuff on the left, leave some room on the left. Okay, this power here, so this power is sigma, okay, so then Boltzmann constant. E is 1. Now the area, since this thing is radiating, those are my blue ones, in every direction, that is 4 pi radius Earth squared, because that's the surface area of a sphere. Okay. And then we have temperature to the 4th. So that's power being radiated away from this huge sphere that is our Earth. And we're supposed to find what that temperature is. So what we're equating that to is the incoming power that's powering, or that's falling onto the Earth from the sun. Those are the red ones. And that would be an intensity, I'm not going to plug any numbers in, times the surface area, but it's the surface area here, I'll write it down. It's the surface area that faces the sun. So we have a sphere, we're radiating out 4 pi r raised to the squared, but the sphere that's facing the sun, of course, is only presenting a circular area to the sun. And therefore that's pi radius Earth squared. This was the intensity. Notice we're not plugging any numbers in yet. We want to solve for t to the 4th. We can see that pi radius squared goes away. So if we take pi divided by 4 sigma, that's an I, not I divided by 4 sigma, right here, is equal to T to the 4th, so I'll take this to the 1/4 power. And then plug it in. The answer will be in Kelvin. Okay, answer will be in Kelvin. Okay, not bad. Oh, and one more thing. The idea is that we've got this incoming energy, we're radiating the energy, the system is in equilibrium. Okay, that's why we have this equal sign. As much as is coming in is being radiated away, that's why the temperature is constant. Okay, and that constant temperature is the one we're finding here. That's the 1/4 power. Okay, excellent. So what are we going to do next? Next, we're going to go back to the heat engines we were talking about. I showed you a bunch of demonstrations last time. Go back to talk about those and their efficiency. So heat engines and efficiency. Heat engines and efficiency. Good. So I'll draw a little picture of a heat engine and we'll clear this up right here. So once again, we had, as an example, that steam engine had a window in the end. We were burning fuel down here. We've got the cylinder with the piston inside, connecting rod, flywheel. So this thing's rotating around doing work, and we have a valve to let steam out. Okay. Just to remind you, and what we're always trying to do is take thermal energy and produce useful work. Okay. So that's what this heat engine is. Device for obtaining work from thermal energy. We put gasoline in our car, and by virtue of this mechanism, we drive around uphill, downhill. If you poured the gasoline on the ground and lit a fire, what would you have? You would just have warmth, but you would not have any work. Okay, so we want to obtain work from thermal energy. And there's that picture to remind you. We also know something about how much is available in fuel. 9 calories, 10 calories per gram. So recall all 1 gram of fuel can have up to Q equals 10 calories per gram. You know, I don't memorize these, so we always just construct them. Okay, 10 calories per gram, and then 4,186 joules per calorie. That's not bad. And if we wanted to have per kilogram, we could say 1,000 grams per kilogram. Grams would cancel, and what would we be left with? Approximately 4.2. We'll just times 10 to the 1, 2, 3, 4, 5, 6, 7. Okay. Times 10 to the 7 joules per kilogram. So I have to put kilogram here as well, okay. heat per kilogram. Yeah, so there's a lot of energy available there. It's some high quality fuel. Okay, but how much of that can we get from our mechanism? This is the amount we have if we just light a fire and heat water up. So how much of this can we obtain from our mechanism? That is the question. And what I'm going to do is introduce a schematic heat engine. Really interesting analysis here. So what we're going to do is talk about heat engines in the ideal sense. So schematic diagram. It's going to be a schematic diagram of the ideal heat engine. Okay. And see what happens here. Schematic diagram, ideal heat engine. And that's what we're going to analyze. So here's, and you'll see this in the book and you'll see it anywhere you look it up. So I'm just going to draw this collection of boxes and circles and arrows first. And this is what we have here. So we refer to this TH as the temperature of the high temperature reservoir from which we draw our energy. Okay? So this is referred to as this top box here is the high temperature reservoir. That's T sub high or T sub hot. It's an H. And it delivers a quantum of thermal energy at this temperature, Q sub H, and this is the engine. It delivers that to the engine, and what does the engine give us? It spits out a bit of work. So work comes out of the engine. For example, when this piston moves forward, makes the wheel rotate, that's the work that we're obtaining. Okay. In the Christmas pyramid, by the way, the candle was providing the heat and the spinning turbine, that was the work. Okay. Okay, but what we found was that a heat engine also always has to give off some exhaust in one way or the other. So that is an amount of heat that is at a lower temperature, an amount of thermal energy at a lower temperature gives it off to what's called the low temperature reservoir. This could, for example, be the atmosphere. Okay. So this is the low temperature reservoir. And the idea is you gave off a certain number of joules to the engine. The engine, by virtue of some physical process, actually delivered some work. And then the valve opens, it has to give off some heat. It's often called waste heat to the environment, which is at, or to the low temperature reservoir, which is at this lower temperature. So high temperature, low temperature, work. I'll write the word work. So that's the schematic. In all heat engines, we try to reduce them to these components. So what's ideal about this? What's ideal about it is there is no friction, there is no heat going anywhere but out the exhaust, so to speak. Okay. There's no energy coming in except this certain quantum of heat, thermal energy at a high temperature. Okay. So these three letters, QH, QC, W, are the full the full set of quantities here. Okay. So ideal engine, let's go ahead and write no friction, comma, no other losses. So what we have for this ideal engine, and don't think I'll miss anything here. No friction, no other losses. What we have is the following. Energy is conserved. So we have QH, that's the energy in, and we have, we'll put the work here first. So the mechanism has some energy coming in, and then it delivers some work plus some energy out. So this is conservation of energy. Okay. We could call this the first law of thermodynamics applied to this particular idea here. Energy, heat coming in, it's either work or it's exhaust. No, nothing else. So yeah, we want to maximize W and minimize QC, obviously. Ideally, it would just be QH equals W, but that's impossible. We'll continue to see why. We saw so far that we had to have some exhaust, and we'll see more of that. But okay, so that's with our ideal engine. So if we want to maximize W, the work, another way of saying we want to maximize the efficiency. So let's talk about the efficiency. We want maximum W, maximum work. Okay. And therefore, we have to talk about efficiency. And the efficiency is just going to be defined as efficiency is the work that you obtain divided by the thermal energy that you put in. So clearly, this number can never be greater than 1. Okay? It can never be greater than 1. If it were equal to 1, that would be the best possible to say. So E is less than or equal to 1. And again, that would be due to conservation of energy. So first law of thermodynamics. Again, conservation of energy. You can't create it or destroy it. First law of thermodynamics. There's a more technical discussion of that in the book, but we don't need that. Okay, so this is perfect. Okay, so how do we get the maximum efficiency? Well, from an ideal engine, which is what we're talking about, ideal engine. I'll go ahead and write E ideal is equal to, now the work we just get from this. Bring QC over the other side. The work is equal to QH minus QC, that's the W, divided by QH. And that, or put that right there, E ideal is equal to 1 minus QC divided by QH. Okay. QH over QH is 1. Okay, so that's the algebra there. So there's our ideal efficiency. Ideal engine. Okay, can we say more? We actually haven't said anything more basically than what we had right here. But the next step is going to use the law of entropy that we have talked about before. So what we're going to do next is analyze this engine in terms of the entropy concept. So yeah, let's go ahead and send this up. And we need a little more room. I'll replace this with a smaller version, just so we have it there. I think we can fit this all on one board. Good. So this is going to be this is the reason we studied that entropy concept. This really delivers a major result. So let's just call this entropy analysis of the ideal heat engine. And we're going to use this result right here. So first of all, let's just draw this TH, QH, there's our engine, spits out some work, QC, TC, and I'm going to put this in a container. Because remember we did the entropy analysis, and we had a law of the increase of entropy for an isolated system. So we imagine this whole thing is an isolated system. And remember the rules of entropy, that the change of entropy is equal to Q over T, temperature in Kelvin. And we had a couple of rules. If the let's go ahead and do this. We've got our little cartoon there. So if energy is entering this body, the change of entropy is positive. Okay. If energy is leaving, so right, or delta S equals minus, I'll do absolute value of Q. We can just agree that the letter Q is a positive value, but minus Q over T, so entropy is decreasing if energy is leaving. So energy in, energy out. But for an isolated system, the second law of thermodynamics was that delta S total is greater than or equal to 0. And change of entropy total is greater than or equal to 0. That's the second law of thermodynamics, and it is equivalent or consistent with thermal energy flowing from hot to cold. That hot to cold is the physical expression of this greater than or equal to sign. Okay. Good. So that's the entropy discussion review. And now what we're going to do is apply. So next, apply this to our engine. So apply to the heat engine. And here's what we get. We have energy flowing out of the high temperature reservoir. So let's go ahead and write it this way, and I'll explain. So we have delta S total is equal to minus QH over TH because it's flowing out. Now the process, what about the engine? Is there any entropy change in the engine? This is part of what it means for this thing to be ideal. Namely, there's no friction, no other losses, and when the engine does a complete cycle, it comes back to the start, which means there's no entropy change for the engine. So I'll put a 0 here. I didn't have to, but that's no entropy change for the engine. Then there's the entropy change for the QC flowing into the low temperature reservoir. So that's the one that gets a plus sign, energy in, so plus QC over TC. And what we know is that this is greater than or equal to 0, because that's the law. Okay. So now we have a relation here that immediately follows QC over TC is greater than or equal to QH over TH. I'm just bringing this over the other side of the inequality. And then I could say that QC over QH, QC divided by QH, is greater than or equal to TC divided by TH. So I have these two dimensionless quotients here. This is QC over QH, and that ratio is always greater than or equal to TC over TH, and which is those two temperatures. So what we're going to do is plug that into the ideal efficiency here. Okay, I can just use this side of the board and continue this right there. Okay, so once more, make sure we got that right. So this was the entropy change of that process. QH over TH plus 0, QC over TC. So we evaluate this inequality, bring the QH over TH to the right side, and then we just rearrange it. So QC over QH greater than or equal to TC over TH. Okay, so we've got that. So we take that into this thing right here. So now for the ideal efficiency, we have E ideal is going to be less than or equal to 1 minus TC over TH. Because I have this inequality right here. QC over QH is greater than this, so if I'm subtracting it off, this ideal is less than 1 minus TC over TH. So this actually an amazing result. Okay, and I didn't leave out a step. This is the proper discussion of this, unlike your book. Okay, this is the right way to talk about it. Good, so that's the ideal efficiency, or the efficiency of an ideal engine, and there's an inequality here, which means the efficiency is always going to be less than this. Okay. I'm going to define something now called the Carnot efficiency. Okay, make sure you remember this is what I evaluated to get that. Okay, so I'm going to erase here. Okay, so there's something called the Carnot efficiency, and we're just basically going to rewrite that expression there. Carnot is the engineer who figured this out first. Okay. So E, the Carnot efficiency, E sub C is equal to 1 minus these two temperatures, that ratio, temperature in Kelvin, of course. This is the maximum conceivable theoretical, but really the maximum conceivable possible efficiency of a heat engine, and it depends on the temperatures between which it runs, the low and the high temperature. Now, you'd like to have your heat engine run at this efficiency, but there's going to be a lot of doing to achieve that. But this is going to be the maximum. And we called this waste heat here, but it's not wasted in the sense that you're making a mistake. Okay? It's just necessarily given off to the environment because of the nature of temperature flowing from hot to cold. Okay, so it's that fundamental. So yeah, this is let's call this the maximum possible heat engine efficiency. And and we'll calculate a couple of examples. In fact, let's immediately do an example. The most humble example would be if we have a system that operates between the temperature of boiling water and the temperature of room temperature. Okay, boiling water and room temperature. That would be the simplest steam engine configuration. So let TC equal, here's what we do. We have to convert to Kelvin. So 20 degrees Celsius equals 273 plus 20, so 293 Kelvin. TH is equal to 100 degrees Celsius. Boiling equals 273 plus 100, so 373 Kelvin. Okay. That's an 80-degree temperature difference. You guys have your calculators. E Carnot for this example is 1 minus 293 divided by 373. You're going to find it's less than a quarter. Okay. So you guys calculate it. You've got your calculators with you. So 80 over 373, question mark, 0.2 something, okay. And that's close enough to discuss because we're heating water up to boiling temperature. Maybe we're directing a jet of steam onto something, turbine, what have you. And yet the most we can possibly get is, a quarter or a fifth, some small amount of all that thermal energy. Okay? And we haven't made any mistakes. Now, if you want higher efficiency, it's difficult to reduce the environment temperature. And in fact, the TC is going to be much higher than the environment in practical terms, okay? Because the whole machinery is generating a whole lot of heat. But yeah, what you have to do is increase the operating temperature. Increase this so you can make this little fraction small as possible and approach 1, but you're not going to approach 1. You're going to be doing really well if you even approach 1/2. So we'll do a couple of homework problems of this idea, and you see this entropy discussion was really powerful because we saw when we were doing this that it really is disconsistent with energy flowing from hot to cold, and yet it gives us such a powerful constraining result. Good. And like I said, I'll assign some problems, and they really always just involve these quantities, right? QH, W, QC, the temperatures, and if they're asking you about power, you have to remember work per time for power, things like that. Okay, so let's see how many minutes we are into this thing. Yeah, perfect. So without further ado, I'll assign a couple of problems. Actually, no, there's one more thing I have to mention because of one of the homework problems. Because of this fundamental relation here, what you have is creative people, engineers and stuff, looking for natural temperature gradients. In other words, natural temperature differences that one could possibly take advantage of to power a heat engine. And one of them is the temperature of the water of the ocean at the surface compared to the temperature of the water of the ocean down low. And that's what one of our homework problems is about. So what happens though is that the temperature difference is not very large, which means the intrinsic efficiency is very, very small, and but it's something to think about. And people do think about it because if you could take advantage of some natural thermal reservoirs, then you'd think you'd be getting the energy for free, so to speak, by just somehow coupling them to some mechanism. Okay, I'll leave it at that. We'll put a couple homework problems on the board here. Homework number, what is this, 42? Just erase this, yes it was, 42. We're in chapter 12 and we just want to do a couple of heat engine problems. 33, gotta make some room so we can read it. Chapter 12, I have 33 and 35 and 44. Interesting problems. Good. See you guys next time.